Okay, so Cheryl, you just sent me this article and my mind is like totally blown. A quantum lie detector? What in the world is going on?
Oh my gosh, Shannon, I know, right? It's just wild. So basically, researchers, mostly from Lighting University, have figured out a way to actually tell if a quantum machine is really quantum or if it's just, doing a super sophisticated classical imitation, like actually truly proving its quantumness.
Wait, so machines could just be pretending to be quantum? That's wild. How do they even detect the lie?
Yeah, totally. So the core of it, right, is something called Bell tests. For ages, these Bell tests have been like the absolute gold standard for proving entanglement and non-locality. These things that classical systems just they can't replicate. It's like quantum's unique fingerprint.
Bell tests. I've heard that name before, but always in like really small theoretical contexts, I thought.
Exactly. That's the crazy part. Usually, they're confined to just a handful of particles, tiny systems. But this team, they just blew that out of the water.
They actually pulled off Bell tests on systems with, get this, up to 73 qubits. 73. That was like seriously thought to be impossible, until now. It's just, I can't even.
73 qubits? Wow, that's a huge leap, right? So, what did the test show? Did the machines pass the lie detector?
Oh, they absolutely passed. The results, they showed clear, repeated violations of Bell inequalities. And that's exactly what you want to see. It's essentially like serving as a physics truth serum. It means those correlations they observed between the qubits, they're not some like statistical fluke or a clever classical trick. They are genuinely, truly quantum mechanical.
So, this isn't just like a theory anymore. They've practically demonstrated it on a pretty large scale, for quantum anyway.
Yeah, Shannon, exactly. It's like we've moved past, is it quantum, to, okay, let's actually prove it with like really robust evidence. It's a game changer for verifying what's truly happening inside these complex systems.
Okay, so if they can prove this quantumness at scale, what does this actually mean for, like, the whole quantum computing industry that's, constantly getting hyped up?
Oh, this is where it gets really important. The quantum computing industry is like booming, right? And there are all these promises of exponential speedups. But how do you, as a buyer or a developer, really know if you're getting a genuine quantum machine versus, something that's just super powerful but still fundamentally classical?
Right, because a really fast classical computer could look like it's doing complex stuff, but it's not truly quantum. So this helps with verification?
Precisely. This new tool gives everyone a much more robust method to verify the quality and the true quantum nature of these machines. Being able to demonstrate Bell inequality violations at this scale, it sets a whole new benchmark. It's like saying, hey, this machine isn't just crunching numbers cleverly, it's actively entangling, interacting, and behaving in ways only quantum mechanics allows. It's huge. Do you know what I mean?
That's a pretty big distinction. So it's about setting a real standard. So, Cheryl, how did they actually pull this off? Because performing Bell tests on 73 qubits sounds incredibly difficult. What was their trick?
That's the genius part. Instead of directly trying to measure all those intricate Bell correlations, which is just super tricky in large systems, they went for a different approach. They focused on minimizing energy within the quantum system, which, funnily enough, quantum devices are actually really good at.
Minimizing energy. So, they just observed if it could get super duper low energy states?
Exactly. And the collaboration was global, which is cool. Leiden University folks like Jordi Tura, Patrick Emmons, and Min Yao Hu, plus teams from Tsinghua and Zhejiang universities.
They successfully created a special quantum state using 73 qubits in a superconducting quantum processor. And the energy levels they measured? Oh my gosh, they were significantly lower than anything a classical system could achieve. We're talking a striking difference of 48 standard deviations. That makes a chance outcome like almost impossible. It's truly, truly quantum.
48 standard deviations. Wow, that's definitive.
Yeah, and this even allowed them to certify a more demanding type of non-locality for up to 24 qubits too. So it's not just quantity, it's quality of quantumness too.